What is an artificial organ? What we do is we try to take human cells, and these do unfortunately come from people who've passed away and donated them, to, just like you can donate your organs, you can donate hearts. And these cells we try to put into an environment that is much like they are in the human body. We've been, and I'm gonna get a little show and tell out here. Oh no, I am so sorry. Oh dear, I'm sorry, I dropped my water. Sorry about that, PJ.
Oh, that's all right.
At least it's not on any of the electronics. But we've been growing cells in these hard dishes for 100 years. Now they're made of polystyrene. 100 years ago they were made of glass. Thank you. I'm so sorry about this, Phil. Thank you. And these dishes, there's nothing in my body that is hard and unyielding like this, not even bone. This is far more brittle than bone. And when we grow cells on things like this, they act like they're growing on a hard, unyielding dish. And so some of the things that we are doing in our lab is we're giving the cells a different environment to grow on. We're giving them soft substrates as opposed to these hard ones. We're giving them external stimuli such as breathing or compacting the cells like they would be compacted in the human body. Your liver is right here. If you take your right hand and poke like right underneath your ribs, you can feel your liver. You can feel that that's a pretty dense organ. And it is not flat. So, for example, if you take primary liver cells and you put them out in a dish like this, they will live for 2 days. And they stop making the enzymes that they need to detoxify pharmaceuticals. So it's really hard to test pharmaceuticals on livers in a flat dish. So one of the things we're doing is we're putting them in constrained environments so that they can be compact and dense, like our own liver. With our heart, and let me see, I'm just grabbing a little bit of show and tell that I can pass around. I can even pass around this hard dish. With our heart, I've got a little bioreactor that is used for our heart. It's a heart-shaped chamber, and it's actually used so that we get that three-dimensional environment that is like the heart shape. And the heart shape and flow actually changes the way the cells behave. I can pass that around too. I definitely want this one back. Try not to knock over the water this time. With our lungs, if you think about our lungs, we've got 2 compartments in our lungs. We've got a conducting zone where we breathe in air, and we've also got a gas exchange zone where the air actually interacts with our bloodstream, and that's our alveolus, or alveolar region. And so we've got like 2 different regions. So we have two different bioreactors that we use to make each of these zones. And I can pass these around. I'm sorry, these are a little wet from water. All of these things I'm passing around are perfectly safe. There's a little water spilled on there, I'm sorry. And there's actually an interesting anecdote about our lung alveolus. I've got a lot of my team here, sitting there, and it's really great. But our graduate student, Tumpa, who's right in the middle here, she is a very, very engaging person. And when she was charged with making our artificial alveolus. And when she first started, she was trying to think about, okay, the alveolus is soft, my lungs are spongy. What possibly could we grow cells on that would be soft and spongy and something that we can use to breathe in and out, or something that we can use to expand. Our lungs expand kind of like a balloon. Well, so she began asking everyone she knew, do you know any good polymers? And turns out she actually got a really good tip from the owner of this establishment, who is a PhD in material science, about using polyurethane, which is soft and yielding and can be used for expansion, much like you would expand a balloon. So that's sort of an interesting little anecdote that involves this very establishment. We also have to think about, if we're going to hook up these organs or join these organs, how are we going to get fluid from one organ to the next? Our vascular system in our body is so versatile. If I'm running, blood goes to my legs. I guess if I'm thinking really hard, blood should go to my brain. But also if I'm running, blood goes to my lungs. We have to come up with ideas in the lab that will solve this problem in unique ways that aren't necessarily the same way the human body does this, because our human body responds like that. But let's say I do need to send blood to the lungs. We use pumps. We have to use pumps to get things from one place to another. And we also have to use tubing. This is some of the crazy tubing that we had in our early models. And I think it's quite spectacular when you think about all these little valves and all these little crimps, and how on earth do I actually get how on earth do I actually, as a scientist, know which valve am I supposed to open when? This is an early version of some of our tubing. And what's really interesting is that a nano engineer on our team came up with a very unusual idea to solve the problem of how do we get fluid from one point to another without making a mess of tubes. And this is something that Los Alamos patented. It's called a fluid circuit board. I can pass one around. And that replaces all of this tubing that we had affectionately called spaghetti. What he was inspired by is, if you drive around town and you see the gas lines, they'll go up from the ground. There's a place where the gas can be turned on or off, and then they'll go back into the ground. And he thought, well, we could do that. So he buried all of these lines into this fluidic circuit board, and they can be controlled by different valves on top. And I thought this was just an ingenious idea. This is not science that happens in a vacuum. This is a science that happens in a big team. Most of my team is actually sitting in the middle of the room here. And so you guys can pipe in any time in the discussion, because I know shortly we're going to open this up to questions and things, and I may actually call on some of you guys. But it happens where we talk to each other and we say, hey, I've got a problem. I'm trying to make this heart do this, or I'm trying to make this lung do this. Just like Tumpa talked to PJ and said, hey, do you know any good polymers I can use?